back to Chem 161. We're going to keep talking about quantum mechanics because that's just what we do. Let's see here. Important stuff to note on the agenda. Oh, lab number 3 is closing tonight, so make sure you get that in. I know some people are still asking questions about it. Make sure you get all those things figured out. I'm going to be busy most of the night, so I'm not going to be super helpful. Let's see here. Yeah, that's pretty much it. We might actually get through all of the important stuff for Chapter 3 today, and then there will just be a bit of cleanup to do on Tuesday's lecture. So I may or may not put the quiz up for Chapter 3 tonight. I'm not really sure. We'll see how far we get. So we'll deal with that later. All right. On the screen here, we have the first ionization energies of all the elements, and we were talking about Tuesday, how we figured out these generic trends, and then how we accommodated for these unusual like drops here. So we said that as n increases, electrons get further away, and so they're easier to ionize because you don't have to lift them up to n equals infinity. It's not as much energy. So each of these n's, the amount of energy is going down. And then as Z effective increases, you're fighting against a harder pull from the nucleus, so it's harder and harder to ionize things. All right. So using those trends, I want you to tell me which has the higher first ionization energy, oxygen or sulfur? Okay. I'll give you 2 minutes to type an answer in the chat, and we'll go over the answer in just a bit. All right, so looks like the popular answer is oxygen, and it is oxygen. Very good. Oxygen is close. Oxygen has valence electrons closer to the nucleus because its highest n is 2. That means to get our electron to n equals infinity to ionize it, would take more energy than it would for an electron in n equals 3, because you can visually see I had to lift it higher. So oxygen has a higher ionization energy. Very good. All right. Which has a higher ionization energy, phosphorus or germanium? You'll notice that I've given you a diagonal pair here, but it should be still relatively easy to predict which one has the higher ionization energy. So go ahead and do that. I'll give you another minute to figure it out. All right. So if we calculate Z effective for both of these and N, so N max and Z effective, so we notice that for phosphorus, the maximum N is 3. For germanium, it's 4. So automatically P is going to win. But then if I do Z effective, I see this. And higher Z effective means harder to pull an electron away. So phosphorus wins on both of these. So for both of those reasons, phosphorus has a much higher ionization energy. So remember, they make that little chart with N max and Z effective, and it'll get you there. So I have a bunch of these now, and I want you to do the same thing. I want you to tell me which has the higher first ionization energy. Now, I've given you one in here that is actually impossible for you to determine. And if you find which one that is, state that it is impossible to determine, and then tell me why you think that is. And if you would like, you can give your best guess, and we'll show why your best guess is probably right, but where the faults in it can occur and why it really is just, like, we have to just do the experiment. So go ahead and do these 4. Let me write down some numbers here. So 1, 2, 3, 4. And I'll give you like 5 minutes to do this because these are pretty straightforward once you know the trends. All right, go for it. one more minute, we'll go over the answers. All right, so let's go onto this screen here. All right, we're going to make a little chart for each of these. So first we'll do Lena, lithium, and sodium. L-I-N-A, Lena. So if I calculate the maximum N, for lithium it's 2, and then for sodium it's 3. And they both have Z effective of 1. All right, which is the higher ionization energy? Well, lower N is higher ionization energy, so lithium's ionization energy will be greater than that of sodium. All right, next we got rubidium and strontium. And that one just doesn't really make a good name. So let's do an Nmax. This one I don't have memorized. I gotta get my periodic table, which is on the floor between my notepad and the edge of the table in a box. How do you store stuff in your apartment, Wes? Everywhere is the answer. Rubidium is period 5, so that's got an Nmax of 5. Strontium is right next door, so that's kind of a wash. We can't really use that. But if we go to Z effective, we get the answer. So strontium must have the higher ionization energy of the two because Z effective is greater for the same N value. All right. All right. Now iodine is period 5, and selenium is period 4. So you might go, oh, look at that. Well, we have a winner, right? Well, let's hold on, because when I do Z effective, I get this, and of those two, this is the better one. Now, before we have said, well, if you have a lower N, that should be the winner, right? So I would predict it to be this one. But if we go back to our chart here, let's do that really quickly. You're going to find out that these are a lot closer than we thought. So where's iodine on this chart? Iodine's right in front of xenon, so he's right here. There's iodine. And then selenium is right here, I believe. Selenium, bromine, krypton. And these are essentially the same value, more or less. I can't really draw a straight line here, except when it wants to randomly draw one. Those are very similar, it turns out, and it's very hard to make a prediction there, because as you get to higher ends, you notice that everything sort of starts to cram together. Like, we've got a lot of spread for n equals 2, but for n equals 5, much less, right? So the N value prediction is really good at low ends, but at high ends, as everything starts to crash together, or crush together, I should say, Z effective becomes a little bit more of a better, accurate predictor. Now, where is the transition where you go from trusting and distrusting Z effective? Who knows, right? We have to do the experiment. So because for this problem, we have... Oops, hold on. I gotta go back to that screen. We have a circumstance where both indicate a strength. The answer is more or less just, I don't know. And in order to figure it out, we have to do the experiment. So it becomes very difficult to predict that one. And so you won't be asked to do that. I put that on there so that we can have this discussion. And that's really it. But the other three are predictable. Because this has an N-max of 2 and this has an N-max of 3. This Z effective is 7, this is 6. And fluorine wins both of these. So I will only give you diagonals where you end up in a situation like fluorine and sulfur, i.e. they're diagonal bottom left, top right. Because that's valid. You have two trends that support it, and you'll get the correct answer. All right. That's first ionization energy. Let's talk about second ionization energy. If you have any questions, though, let me know. We've already talked about these exceptions, so I'm just going to kind of breeze over them. But remember, the first time you have an electron pair that is present, the ionization energy for that element is slightly lower than the previous one, because the electrons push each other out. And then when you go from S to P, the p orbital is slightly easier to ionize for the first electron because it's higher in energy. So again, those are our exceptions. So the first paired electron is lower than energy than the previous one. So group 16 versus group 15. And then hopping from 2s to 2p means you jump up in energy. And so it's easier to ionize 2p. All right. Now, when you take away the second electron, all the remaining electrons are... I'm sorry, let me start that again. When you take away the first electron, all remaining electrons are then pulled by the nucleus even tighter. Because the charge from the nucleus is distributed over a bunch of electrons. If I get rid of one of those electrons, that force is effectively on fewer electrons. And so each of them is attracted to the nucleus. And they actually sink down in energy just a little bit. So they all get slightly closer to the nucleus. This is also due to the fact that there is less electron-electron repulsion pushing all the electrons apart. Now, in some cases, the ionization energy for the second element jumps up very little. But in other cases, it jumps up a lot. And by a lot, I mean like 5 to 10 times or more. Generally speaking, like a small jump might be like less than double. Or something like that. Now, the reason that this happens is because if you remove electrons from a core layer, or what I should say is an electron that was a core electron before you removed all the valence electrons, the ionization energy will be a lot more. And so we can see this in action right here. So here are some ionization energies for two elements, sodium and magnesium. Sodium has one valence electron because it ends in 3s1, right? If we get rid of that, we have to pay this much energy, 496. That's not very much. But if I get rid of the second electron, which was in this, I'm going down a layer. Layer 2 is much closer to the nucleus than layer 3 was. Therefore, it's going to require a lot more energy to get it relative to the first one. For magnesium, here's its electron configuration. I'm just ignoring the first few because we don't get that far. When I get rid of these two, that requires some energy, but the next one is way more. So if you have a mystery element and you see that your energies are like, okay, first IE is this much, and then the second one is this much, this much, this much. Like, this looks pretty normal, right? And then, whoa, what happened here? Why is that one way more? And the answer is, well, these must have been valence electrons, and then this must have been a core electron. So by looking at the data, you can actually identify what an element is by saying, oh, there are this many valence electrons. I can write out an electron configuration. Which one or what would the fifth electron have been? Oh, it's a core electron. So, okay, this element must be, and then you could predict it. Why might I ask you or tell you about the scenario? Because we're going to be predicting an element based on this information. So, that'll be on page 2. We're going to get to that in a second. But what I want you to do here is I want you to rank each of these atoms in order of increasing first ionization. Now, you're going to notice that I've sort of scattered them all over the periodic table here. But what you can do is you can write a giant chart that has Z effective and N max, and you should be able to pick any two and compare them, and then pick any other two and compare them, and then get all of the data that way. Okay, so these are doable. And then down here at the bottom, rank these ions in order of increasing ionization, first ionization energy. This should be pretty straightforward too. So go ahead and do these problems. We'll go over the answers in about 4 or 5 minutes, and then we'll go on to the next set of problems, and then we'll talk about electron affinity. So see you in a bit. One more minute, we'll go over the answers. All right. So if I write out, so we'll go like this. If we make like a chart that we just like these that are on the screen. Well, there were on the screen until I erased them. We can rank these pretty effectively, it turns out. So I'm going to just go calcium, krypton, arsenic, and potassium. And we'll go Nmax and Z effective. So calcium, oh, I need my periodic table again, which is, oh, now it's over here. I'll just put it right here, I guess, for now. So calcium is in period 4, Z effective 2. Krypton's in period 4, Z effective 8. Arsenic's in period 4, Z effective 5. And potassium's in period 4, Z effective 1. So this is pretty straightforward. They're all in the same Nmax, so I'm just going to sort them by Z effective. So I want this in order of increasing. Be careful here. So I got to start with the lowest. So that's going to be potassium. And then calcium. And then arsenic. And then krypton. All right, we can do the same thing for the second one. You'll notice that these are all in the first column. So sodium, cesium, rubidium, potassium. Yeah, if you did them backwards, it means that you definitely got the trend right, but I asked for increasing and you gave me decreasing. So be careful because you never know what the problem's going to ask you. It could be list in order of decreasing. And it's hard to say. So these are all +1. So that's not going to help us, but this will help us. So this is 3, this is 6, 5, and 4. And we know that the larger the N is, the lower its ionization energy is. So I want to do it in order of increasing. So I would say that cesium has the lowest, then rubidium, then potassium, then sodium. They're all going to be pretty low, but the lowest is going to be cesium. All right. Now I've given you like this sort of staircase going on here. So I got chlorine, bromine, argon, and selenium here. And so chlorine and bromine have the effective 7. Argon is 8, and selenium is 6. And then what ends are these? So 3, 4, 3, 4. So we've got all sorts of crazy shit going on here. How the heck do we do this? Well, let's look at the 2 that are in 3 and then the 2 that are in 4. Because we don't have any diagonal going top, left, bottom, right, so we should be able to just compare the 3s and the 4s, and then we can compare the ones with the same Z effective, right? So I would know that between these two, chlorine and argon, that this must be true, right? Because they have the same N, but Z effective is greater for argon, so argon must have a higher ionization energy. And I could do the same thing between bromine and selenium, right? They're both in group 4, or I'm sorry, they're both in period 4. They have an N max of 4, but bromine has a higher Z effective than selenium, so this must also be true. And then I also know that if I compare the two between, or the two that have Z effective of 7, that this must be true. Because N max equals 3 is a higher ionization energy than N max equals 4. And so now I can sort them. Because I know that bromine has to be less than both of these. So I can go like this. And I know that selenium is less than that one. So there's the answer. So selenium must be the lowest, then bromine, then chlorine, then iodine. Or not, bromine, then chlorine, then argon. Sorry, I don't know why I said iodine. All right, we can do the same thing down here. But really, these are just going to be, okay, which one has the most electrons and which one has the fewest electrons? So we know that C minus has the most electrons, so it's going to be the easiest to remove one. And each time you remove electrons, it gets harder and harder to ionize them, right? So it'd be like taking first, second, and third ionization energies and looking at those numbers. And the same thing for the sodiums here. So easiest to ionize the one with the most electrons, and then this would be the next ionization, and then the next one still. So really, I've sort of just disguised this question as looking like first ionizations, but really it's just a second, third, fourth, etc. All right, so that was the first set of problems. Here's the next set. All right, way back at the start of the quarter, I dropped cesium metal and sodium metal in water, and we watched sodium metal fizz around and burst into an orange flame, whereas cesium metal immediately exploded. Like 1 or 2 frames on the camera. So based on what you saw in that video, and based on what you now know about quantum mechanics, why does this happen? And my hint for this is, in order for the reaction to occur, the metals have to become cations. So you should be able to answer that now. And then the second question I have is, here are a bunch of elements in period 3. Here are some ionization energies. What element goes in the mystery element spot right here? What is the mystery element based on this data? All right. I'm going to give you 3 minutes to do this because these aren't terribly difficult. And then we'll check in. And we'll talk about electron affinity real quick. All right, one more minute. All right, so if I go over here to this diagram right here that I've just drawn. Hold on, let me get the question I'm looking at in the frame here. If I draw in my electrons here, n equals 3 would have an electron right here in the 3s orbital. N equals 6 would be up here. The energy required to ionize n equals 3 would be this much, but the energy required to ionize n equals 6 would be much, much, much less. The less energy it takes to ionize something, the more energy you have to do other things, such as ionize other elements that are present around you. So if I don't need that much energy to ionize cesium, all the energy that I get from doing the reaction can then be used to ionize other cesium atoms. And so you'd see that cesium should go a lot faster because you can do a lot more with the small amount of the small cost that you have to invest for it. Whereas sodium takes a second to get going. So it comes down to ionization energy. Cesium is more reactive because its ionization energy is lower. All right, if we go back over here, what is the mystery element? How do we determine this? Well, let's look for the giant jump. So I've got ionization energy 1 to 2. So this increased by like a factor of 3 or so. This didn't increase by more than a factor of 1. So it didn't quite double. But then this is almost 5 times as much. So I would think that based on this data, that the big jump would be between the third and the fourth electrons. So there must be 3 valence electrons. This must be a core electron. So based on this information, what element is in period 3 and has 3 valence electrons? It's aluminum. All right. And I know this is aluminum because I literally went to Web Elements and copied these numbers when I wrote this slide. All right. That's ionization energy. When we come back, what we're going to do is the opposite of ionization energy, which is electron affinity. Electron affinity is just, hey, if ionization energy is moving electrons up to n equals infinity, electron affinity is just dropping the electrons back in there and seeing what happens. We'll deal with that in just a little bit. But for now, we're going to take a break. Oh, break is over because I never reset it from the previous class. There we go. It's been really nice out lately. Yesterday was really windy, so that made me play this for my classes from the Stardew Valley track, and we're going to do that again today, so I hope you enjoy. Hi, everybody. Hope you had a good break. I went out into the living room and discovered that my cat was eating a plant that I did not want him to eating, and that he has eaten almost all the leaves on it, so I put it outside where it is lovely and sunny, and I hope that my plant will be safe, because cats are a menace. I love them anyway. I said that as I turned around and looked to see if there was a cat listening to me, but there was not. All right. We're going to talk about electron affinity now. Electron affinity is the opposite of ionization energy in terms of like what we're doing. So if I go over here to this not this diagram actually, but this diagram that we've had forever, ionization energy would be me taking some electron. So let's just draw. Here's sodium. This would be, well, let's actually put sodium in here. So there's sodium. This would be the ionization energy, or the first ionization energy of sodium. The electron affinity would be doing the opposite of that. So if I hadn't done this, and instead I allowed an electron to fall down, this would be the electron affinity for sodium. Now, depending on where we are putting the electron will either stick, and we will get some amount of energy back. So electron affinities tend to be negative. So we'll write that. Tend to be in terms of energy, because the electron is falling. Lifting the electron would be positive. An electron being dropped in should be negative. Now, it might not be that negative. It might be relatively close to zero. But, just like with ionization energy, there are exceptions that occur. And those exceptions are best illustrated if I show you the chart of electron affinity, which unfortunately I didn't put in the slides. So what I'm going to have to do is find it in the textbook real quick. I already have the textbook open. So let's see here. Chapter 3. At the end of quantum mechanics is... Where's my electron affinity chart? Those are first ionization energies. Those are... There we go. That's what I want. I don't want to update this. No, go away. Can I click somewhere? Oh, my goodness. There's a pop-up in front of my table here. I could scroll it down, and hopefully that'll be far enough away. I'll just make this real big. All right. Now, you can see some asterisks here. Asterisks are calculated values, which means that the experiment could not be done effectively. And the reason for that is because the electron just doesn't stick. It bounces off. So, when you add an electron to an atom, the energy is refunded a little bit based on how far it falls. Now, in some cases, you could see you get a really, really positive number, or at least more so than expected. For some of these cases, it's pretty obvious what's going on. So what I'm going to do is I'm going to make this really small and put this up here. And we're going to look at some of these cases. So first, let's just undo everything I just drew in here. Boop, 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 boop. I can't undo everything I drew, so I could just do that. All right. So if I put this up here, all right. So we're gonna look at elements in period 2. So the first element I'm going to look at is neon. This is neon. It's got 10 electrons, and you can see that neon very, very, very barely wants an electron. And the reason for that is if I add an electron in here, well, everything in levels 1 and 2 is full, right? So I'd be adding an electron to n equals 3, And it's hard to do that. So noble gases won't accept extra electrons easily. They have a really high Z effective. Z effective is 8. But when I put this extra electron in here, all those 2s and 2p electrons become shielding electrons. And Z effective for this electron is effectively 0. So the electron falls pretty far, but there's very little force pulling it towards the nucleus. And therefore, it doesn't stick. All right, so that's the noble gas. So we got that one. Let's now look at... So chlorine and oxygen makes sense. So there's chlorine, there's oxygen. Let's look at nitrogen. When I drop the electron in for nitrogen, I have to pair it. And remember what happens when we pair electrons. With ionization energy, the electron-electron repulsion pushed the electron away, so it was easier to ionize, right? With electron affinity, what ends up happening is that the first pairing, or the first time we pair an electron, I should actually write YAAAY, I guess. When you pair the electron for the first time in that p orbital, the electron affinity is much less negative than you'd expect from its neighbors. And you can see from these numbers right here that carbon and oxygen accept an electron really readily. But the first time I drop an electron in there and it ends up being paired, that number is abnormally less negative. 0 is much less negative than where we would expect it to be, which would probably be like minus 130. You see the same thing for phosphorus down there too. Phosphorus should be between negative 120 and negative 200, but instead it's negative 74, and that's due to electron-electron repulsion. And then the last weird thing is in group 2. When we add an electron to the elements in group 2, so let me get my eraser out real quick. Oops, there we go. So let's get rid of these. And we're going to drop this in here. Now, I'm going to write 2p, but in general, I mean the p orbital. The first electron that you drop into a p orbital is just too far away from the s orbitals and the rest of the nucleus for the nucleus to actually attract it. So everything in group 2 has a super positive electron affinity. Those elements just do not want extra electrons. If you try and stick an extra electron on beryllium like this, the nucleus just doesn't see it. It's too far away. So those are our exceptions, but the general principles is that electron affinity increases as Z effective increases. And that makes sense because if we're dropping electrons in, the higher Z effective is, the more the electrons are pulled. And then the farther the electrons fall, so we'll say a farther fall, so they're going to drop into a lower N, means higher electron affinity. So now you can more or less predict this entire chart. Now there are some interesting exceptions. For example, fluorine and chlorine. Chlorine has the highest electron affinity, even higher than fluorine. And the reason for fluorine's not being the highest happens to be that it's just so small. Fluorine is so small that adding another electron in there, fluorine really wants that electron, and it'll take it. It's happy to have it. But it's not as happy as chlorine because there is a little bit of electron-electron repulsion due to just how crammed in all those electrons are around. the n equals 2 layer. N equals 3 gives us a little more space so that you get a little more energy back. I'm not going to ask you about that particular exception or any others that are beyond what I've written on the screen in green here. So we should be able to make all these predictions based on writing out the electron configuration and then looking at the trends. Is there a reason the chart doesn't show the electron affinity for transition metals? You know, I don't actually know the answer to that. I assume that the transition metals will accept electrons and they'll be all roughly the same amount. There might be some oddities with like pairing electrons and stuff like that. I don't know why they didn't put them in here. I'm pretty sure that they would exist. Like, we could look them up on Web Elements if we had time. But yeah, I don't have that information, unfortunately. All right. So, like we said, generally speaking, the electron affinity is negative, and it becomes more negative for high Z effective. Now, just like there's an electron affinity 1, there is an electron affinity 2, 3, 4, etc. And that would be the second electron you add, the third electron you add, the fourth electron you add, etc. Those numbers do exist. Those numbers can be surprisingly weird, so we're not going to discuss them. Really, if you want to predict the second electron affinity of an element, you have to do the experiment. All right, and these are all the trends that we just talked about. And there's more trends. All right, so using that chart that I just showed you, in fact, what I'm going to do is I'm going to just put this back on the screen here for you. Oh, we don't need this, though. I want you to tell me, in each pair, which one has the more exothermic electron affinity. Exothermic means more negative. Can I put the whole thing on here? Well, you can't see it all if I do that, so we'll just do that. Beware of exceptions, because I hit like 3 exceptions here, so I try and do one of each. And really, that's all I'm going to care about for electron affinity is, do you know what it is, and can you pick the exceptions? So try not to just refer to the numbers. Use the trends that we've discussed and the quantum mechanics behind them. We'll go over the answers in like 3 or 4 minutes, and then we have a surprise. One more minute, and we'll go over the answers. All right. So let's go back over here to this screen. We're going to make a little chart, but I'm going to add, oops, well, you can't see half the chart. There we go. I'm going to add this extra little column here, exception, just to see if we land on any of the weird things that are going on. And we'll show you how we'll deal with that in a second. So these are both 2. We're doing electron affinity, so we'll just indicate that. So what we would normally say is we would say, okay, the lowest possible N and the highest Z effective should have the highest exothermic electron affinity, or the most negative. Now what we're going to do is I'm going to draw out this for each of them, and we'll see if we hit an odd exception. Are we the first electron in here from 2s? I guess I should draw 2s also, huh? So for boron, that looks like this, and for carbon, that would look like this. And so the electron we'd be adding would be this one or this one. Neither of those are weird exceptions. We didn't add the first one in 2p, nor did we pair them, nor did we have to put it in a higher N. So everything checks out. So carbon should be the one with the more negative electron affinity between the two, and it totally is. Okay, let's do that again for sodium and potassium. All right, so there's what we got. Lower N should be the higher electron affinity. I'm just doing this with it. Nothing, no problem here. Everything works out. All right, let's do the next one. So we got bromine and krypton. So bromine has Nmax equals, I don't know, I have to look it up, 4. Same with krypton. Now, looking at this, you might say, oh, look at that. There we go. That's going to be the end result, right? But I put too many boxes there. Let's undo that. So here's what bromine will look like with its electrons in the valence shell. And here's what krypton would look like with its electrons in the valence shell. All right, so let's add in the next the electron that we're going to electron affinity. So bromines would go there, but kryptons would have to go into 5s. It'd go to the next layer. So exception. This is the correct answer. It won't stick because 5s is too far away. All right, let's do the next one. So we got silicon and phosphorus. I really shouldn't have to write out these labels each time, but I'm just doing it because That's just what I do. Okay, so silicon is in N equals 3, so is phosphorus. Z effective is 4 and 5. And if I draw out my orbitals here, so 3s, 3p, 3s, 3p. Here's silicon, 1, 2, 3, 4 valence electrons, 1, 2, 3, 4, 5 for phosphorus. I'm going to add in the next one for phosphorus or silicon, no problem. I'm going to add the next one in for phosphorus. Ah! It's the first pair. Exception. This is the answer. Remember, only the first pair does this for electron affinity. And then finally, magnesium and aluminum. I'm just going to skip the column labels this time. These are both in period 3, so they have N equals 3. And we really don't need to do any more than this. Doo-doo. There you go. But if you really wanted to rationalize it out a little further, so 3s, 3p, these are labels I'll put in. Here's what aluminum's looks like. Here's what magnesium looks like. Oops, that's not where that would go. It would go over here. But this one, uh-oh. First in a p orbital. Exception. And we picked aluminum anyway, so that's fine. If I had given you instead sodium and magnesium, you would also still pick sodium because you hit an exception. And the exceptions just trump everything in this. If you hit an exception for any two that I'm going to compare, pick the other one. It'll always be the right answer. All right. Looks like we did all right. All right. We now have a very important surprise here, and the surprise is, hooray, congratulations, that's the end of quantum mechanics. The only thing that we can do is celebrate. Woo! I hope you enjoyed that. All right, let's get back to work. The rest of Chapter 3 is 140 stuff. You already know all of this, so we're going to go over it pretty quickly in the last 30 minutes. In the periodic table, we've discussed tons and tons of trends so far that all have to do with like quantum mechanics and weird oddities that all have to do with electronic structure. And the entire reason for the periodic table that we totally glossed over in Chem 140, for good reason, you could teach an entire class on this shit. And in fact, if you're taking 300 level chemistry, there is an entire class on this shit. Guess what it's called? It's called quantum mechanics. But the whole point is, all of this stuff that we've discussed, all this Z effective, N, L, M sub L, M sub S, all of these things built the periodic table. And before these things were discovered, these quantum properties, really just observations of the elements were enough to get us halfway there. And that's what this guy did. This is Dmitry Mendeleev. Dmitry Mendeleev noticed a lot of different properties with elements and their reactivity, and he compiled all of his observations into a periodic table that you could reference so that you didn't have to memorize it, other chemistry faculty. Yeah, I'm calling you out. Don't make your students memorize the periodic table. That's what it's here for. Womp womp. Sorry. I find that's a pet peeve of mine, is instructors that make their students memorize elements. Literally, that's what this guy did. You're undermining Dmitry Mendeleev. Look how sad he looks. This is the face of somebody whose life work has been discarded because somebody wants you to memorize the first 20 elements. Like, that's silly. Use the periodic table. Now, because of all these predictive properties, it was possible in Dmitry Mendeleev's time to predict elements that didn't technically exist as far as people were concerned. Like these two elements right here, gallium and germanium. Wow, I forgot all about that. It won't let me draw a circle. Gallium and germanium hadn't been discovered yet, but you could predict their properties based on the elements that were in the same column as them. So you could, if you had found aluminum and indium, and aluminum's super common, silicon's super common, you could predict the properties of each of these elements based on the ones that are on top or beneath them. And so we can do that because all of these elements share something in common, and that thing is their electron configuration. Everything in group 13... you know what? We're not going to write this on this screen. Or I can write it up here. It's fine. Everything in group 13 ends in this electron configuration. Everything in group 1 ends in this electron configuration. So the periodic table is completely arranged based on electron configurations. Everything in a column ends in the same electron configuration. I mean, at least until we get to the exceptions for all this stuff here in no man's land, which is usually right. So, for instance, anything in group 7, or actually, let's not pick group 7, that's a weird exception. Anything in group 5 should end in D3. And as long as we don't land on an exception, it will. Everything in the main group elements, though, groups 1, 2, and then 13 through 18, does follow this pretty well. So, we're going to formally call those things groups. Groups are columns on the periodic table. Groups are numbered 1 through 18, but there is an old nomenclature scheme that has 1 through 8A and then 1 through 8B. We're going to try and avoid using that, although some of my slides do refer to these, and I haven't quite gotten them all out of there yet. The AB nomenclature was Mendelev's notation, and there are some useful properties for the AB notation, but ultimately I've just abandoned it, and so is the rest of the world. They dragged me kicking and screaming, like, no, I want to use A and B! Ah! Fine, I'll use 1 through 18. And so now we just use 1 through 18. Elements in the same group tend to have similar reactions because they have the same ending valence electrons. Everything that ends in S1 reacts the same. Everything that ends in S2 reacts the same. Everything that ends in P6 reacts the same. There's our naming schemes. If you go across the periodic table, left to right, we call those periods. So, across is periods. The main thing of interest for the period number is the period number tells you the highest principal quantum number in which the valence electrons lie. So if I go back to the periodic table here, oops, that's not how we go back to the periodic table. Everything in row 5 has n equals 5 as its valence layer. Everything in row 3, n equals 3 is the valence. So there is absolutely a method to this madness, and now you know it. Alright, let's just go over here. There are different names for columns on the periodic table. I'm going to cross out 2 of them because this name right here, pnictogens, I literally did not know that that was a name until I saw this textbook like 2 years ago. So nobody gives a shit about that. I'm also going to cross out chalcogens because as a student, I never heard this name. So if I didn't hear it in 10 years of studying and my first encounter of it was in chemical literature, you don't need it for an introductory class. If you specifically study oxygen, sulfur, selenium, tellurium, then sure, call them chalcogens. But if you don't, nobody cares. The other names are common enough that they're worth knowing. And so that would be everything on the screen here. You heard me just refer to things as main group elements. These are the main group elements. in groups 1, 2, and then 13 through 18. The main group elements are modeled best by all the stuff we talk about in chemistry. So when we're talking about, like, oh, does it follow this electron configuration model? Or does it follow number of valence electrons? Or does it follow the octet rule, which we're going to talk about in Chapter 4? We're referring to main group elements because the answer to all of the elements in those groups is yes. For transition metals, lanthanides, and actinides, the answer is maybe, probably not, or no. We're not a fan of maybe, probably not, or no in introductory chemistry, so we get to that in a 300 or 400 level class. Otherwise, the groups as listed are important to know. Alkali metals and alkaline earth metals are named such because when you put them in water, they make bases. So they are alkaline. Halogens and noble gases are common. Noble gases are unreactive. Like all nobility, they sit on their asses and do nothing. Noble gases don't do chemistry. Of course, there are always exceptions. We'll talk about those maybe. We will talk about those, actually, in Chapter 4 a little bit. And then lanthanides and actinides are only interesting if you are me. Specifically, I worked in a lab at UC Irvine that only did their chemistry with lanthanides and actinides. I got a very special actinide to do all my work with. It's called uranium. You've probably heard of it. Yes, I have been exposed to uranium. I probably have ingested some unwillingly. There is more uranium in my body than average. Congratulations, Wes. That is not something to be proud of. Womp womp. All right. But yeah, just know those names. This is trivial. I'm not going to have you guys do this because spending 5 minutes on name, period, group, and then give it a label. Yeah, you could do that on your own time. You did it in 140. I just want to get through Chapter 3 here. Finally, we can split the periodic table into metals and nonmetals. You have seen this slide in 140. It is exactly the same, including Bender. A metal has to have all of these properties. A nonmetal has none of those properties, and a metalloid has some of those properties. How do we define these on the periodic table? There's this squiggly line that most periodic tables have. I need a better color to do this. Let's do dark blue. This is the metal-nonmetal line. And it basically separates out all the metals on the left from all the nonmetals on the right. Anything that touches the metal-nonmetal line, with some exceptions, so these are our exceptions, is considered a metalloid. What are our exceptions here? This one is aluminum. You know, I should just draw the elements in the boxes rather than draw X's through them. So we've got aluminum, which is important. Aluminum we consider a metal. Polonium we don't care about because it's radioactive. And astatine we don't care about because it's radioactive. So these you don't really need to know. But this one's important. Aluminum's a metal. Everything else that touches the line that isn't radioactive, we call metalloid. Hooray! Here's some pictures of elements going left to right. Or I'm sorry, right to left, actually. You could see that if we go along period 3 here, we start with something that is very obviously not a metal by virtue of it being a gas. This is at least a solid, but it doesn't even look shiny. And it also looks pretty fragile. These are definitely metals. I can do the same thing going vertically. This is group 15. Same thing. All right. Hooray. We've discussed the periodic table. This last section is just going to be our segue into the next chapter, which we're going to start next week, Chapter 4. And again, I am going to go through this pretty quickly, because at this point, you should know how to form an ion. What element will form what ion is governed by how many electrons they have. We're going to talk about this more formally in Chapter 4. But for our purposes, becoming isoelectronic with a noble gas is good enough. Really, the definition that we want is full S and P subshells. This is a better definition. And it is not a definition I gave you in Chem 140, because you didn't know what S and P subshells were back then. Well, if I draw selenium's electron configuration, selenium is in... Selenium is in period 4, and so it'd look like this. There's selenium. Again, I only care about S and P, that's why I scribbled out 3D, but this would all be full. If I wanted to make an ion out of this, I need to fill its S and P subshells. So I would go like this. Boop, boop. And this is the ion we would form out of it. Now, you probably remember this from 140 by me going, oh, well, I drew valence electrons, and then how... Oops, hold on. Sorry, I drew 6 valence electrons. How many more do I need? Oh, I need 2, right? This is chapter 4. We're going to do this in chapter 4. But the real reason behind it has to do with... subshells. I meant to write subshells. I gave up. If you can fill your S and P subshells for your valence layer N, you will create a stable ion. And we've done all this in 140. It's just, this is actually the reason behind it. All right. What about barium? What if I do this for barium? Well, here's barium. I'm going to draw a little bit more for barium, though. So barium's in row 5, so I'm going to go like this. 4s, 5s. I'm doing this in the wrong order, I realize. Now, you know what? Don't be dumb. Do it in the right order. And yeah, there's d electrons in there, but nobody cares. So here's what barium would look like. How do I get a full S and P subshell? Well, I have 5 p orbitals, but I'd have to fill in all these electrons to do that. Here's an easier way to deal with this. Is instead we just go bloop. Just get rid of those 2. And then here is my full valence shell for S and P subshells. So the ion we would expect would be barium plus 2. Oh, barium's in row 6, so I wrote the wrong numbers. It should have been 5s and 5p and 6s. Oh well, whatever. I accidentally did strontium, but same idea. Now, in 140, I told you that we can't predict transition metal charges very easily. But now we've studied electron configuration, so this part we can actually do. So for instance, we can create something that has full S and P subshells, and that ion will be stable. And then we can start picking out the d electrons and seeing if we can do stuff to get other possible combinations that might make sense. So let's try this for iron. And so what we're going to do is I'm going to write out iron's electron configuration. So iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. There we go. So I'm going to draw this part right here. So we'll do 3s, 3p, and then we'll put 3d up here, even though it's not that much higher. and then 4s. And I'm not really doing these in the right order. That's okay. Because all these energy levels change anyway, and that's... All right, so 4s2, 3d, 6. So the first thing that we can do is we can say, okay, well, if I get rid of these, I now have a full n equals 3 valence layer. So I would predict that Fe2 is common. And it totally is. Iron 2 is one of the most common forms of iron. Now, if you wanted to go one step further and say, oh, is there anything else I could do to make this even more stable? Well, you do have a paired set of electrons here. I could remove one of those for you. And then this is still valid. It's just now I have less electron repulsion. So maybe iron 3 is common. And it turns out it's even more common than iron 2. So you can make some predictions based on quantum mechanics. Look for things like electron-electron repulsion in a paired orbital. But first and foremost, ditch all of your 4s electrons so that you have a full s and p subshell. In other words, every element in the transition metals rows, except for the ones that move an electron up from the 4s to the 3d, they should all be +2. The other ones should make a +1. Or at the very least make an odd number of electrons. And it turns out that they totally do. Now, this is sort of a curiosity really for our purposes because it's hard to make these predictions to any degree of accuracy without actually looking at the period, or not looking at the period, without actually doing the experiment. But if you've always wondered, like, how the heck do I know which configurations occur for metals? Now you have a better chance of predicting that. All right. These I'm going to leave for you to do on your own, but I will write the ions out here in case you want to do this practice. So there's the answers to those. And then these, you could predict what ions form. And again, they should all form 2 pluses. So 2 plus, 2 plus, 2 plus, 2 plus. This one is the one exception. You're going to get 1 plus. And the reason for that is, remember that copper does this. Because it ends on D9, so we moved an electron. So if I get rid of this, now I have a full S and P subshell for 3S and 3P. And so this is the charge that we get. Interestingly, copper 2 also does exist. But for silver and gold, silver 1 is the only one that happens. Gold 1, the only one that happens that we care about. So yeah, we can predict those. Monatomic versus polyatomic, I mean, kind of duh. Is there one atom in the ion, or are there multiple? So this would be a monatomic ion. This would be polyatomic. And yeah, I am rushing through this because we're sick of Chapter 3. But we're going to talk about more stuff in Chapters 4 and 5 that deal with ionic versus covalent. You should remember ionic versus covalent from 161. These are all just slides from 140. Sorry, I should say, you should remember all this from 140. So you can review these on your own if you'd really like to. You should be able to make ionic compounds together. And then I think that might be it. Oh, just properties of stuff that you can read. So, yeah. So, yeah. I will paste these links into the chat in case you want to see them. Oops, that's not how I do that. Hold on. So, let me go back to where that was. So, if you want to see the formation of sodium chloride, I'm not going to actually play this out for you because you've seen Lonnie's lab when I did this last time. So, we'll hit share, copy, paste. Formation of NaCl from elemental Na and Cl2. So there's that link in case you want to see that. That'll show up in the chat, which you can click on. And then I have another demo here. This shows the conductivity of an ionic compound when you melt it, which this is actually kind of neat to do. So this is molten NaCl is conductive of electricity. So that's there in case you want to look at it too. And really, the rest of this you can just read. There we go. We did it. You can read the summary too. I just don't care. I just wanted to get through with Chapter 3 because it's so freaking long. But that's it. That's Chapter 3. Now that we're done, everything feels empty, right? It's almost like nothing is there. There's nothing else to talk about. In fact, if I just turn it all off, maybe we'll just feel peace. No, this is weird. Let's just end the lecture. All right. I want to thank everybody for coming out to the end of Chapter 3. We're finally done. So next week, we will not be in Chapter 3 forever. We will do Chapter 4. Chapter 4 is kind of the last chapter, because Chapter 5 takes like 20 minutes. Yeah, I don't actually have the orc in my slides for 161 for some reason. I need to go and edit him back in there. But there definitely needs to be a celebration orc somewhere. Anyway, hooray, we're all done with Chapter 3. Now go finish lab worksheet number 3 if you haven't done that, because that will be due later tonight. It will close. And then over the weekend, make sure you're doing Chapter 3 homework practice, because the quiz for Chapter 3 I'm going to post later tonight. That'll be due next week. The quiz is really long because Chapter 3 is really long. It's got a lot of little questions, so make sure you're on top of this stuff and ask me any questions you might have. I hit play and nothing happened there. Why did nothing happen? There we go. That's what I want. Yeah, that's all I got. Go and enjoy the sun, and no more quantum mechanics. Hooray!